Okay, now let's discuss the concept of embedded computers. Basically, embedded computers is a combination of hardware and software which is designed to carry out only a specific task or specific set of functions. You may be familiar with some sort of embedded computers around you. For example, the air conditioning system that you're currently enjoying, or the onboard computer in your car's fuel injection system. These are all different types of embedded systems, and they are supposed to be they're actually computer systems that are meant to carry out on a specific task. They're not using for general purpose processing. By general purpose processing, we mean that our computer, that our personal computer, it can be carried. It's this computing system that is can be used and carried out various tasks. But if we're looking at your specific processing, then we're looking at your embedded computers. Okay? Now, basic components of embedded computers, different types. Basic principles of embedded processing can involve microcontrollers, microprocessor, or systems on chip. Basically, microcontrollers, it has a CPU, and apart from that, it has RAM, ROM, and some peripherals that can be connected to it. Okay, and all of these components are part of a single chip, and they are together they carry out a specific task, right? So for example, if you have some sort of toy that is capable of executing some fixed number of instructions, and apart from that, it can take some inputs of predefined instructions, you can program a toy to it to do specific tasks, in which case that is using a microcontroller. The predefined task that is capable of doing are stored on the ROM, and anything that you feed into it, that the sequence of events that will be carried out according to you is fed into the RAM. And according to that, and you're obviously using some sort of method to input this data, and all of this combined is known as a microcontroller. Similarly, a microprocessor is something else. It's an integrated circuit which only has a CPU. There's no RAM, there's no ROM, no peripherals, and these can be added later. But on its own, it's just a single microprocessor, it's just a single CPU. But a system on chips is actually the most advanced version. It has CPU, it has the memory, input output ports, secondary storage, all connected to a single microchip. All one part of this complete chip. Now, micro systems on chip is the current Mac Apple M1 processor from Apple Silicon is a very good example of systems on chip, because it is a single chip. The M1 chip has everything connected to it. It's all part of the single chip. The RAM, ROM, and the processor, everything, hard disk, everything is part of the same chip. So this is known as system on chips, right? Okay, now basically your embedded systems operate on this basic principle that we have an embedded system right here that relies on some software hardware. It has a user interface in which allows us to interact with it. And then it takes some sort of analog or digital input. If it's analog, it's obviously using some sort of sensors. The system requires the principle of feedback. So for example, it's an air conditioning system. The feedback means that it's giving some output. It is sending out cool air, and then it is determining if the temperature has reached the desired level. And if it does see the temperature has reached the desired level, it'll turn the cooling off. So the feedback means that every action that the system takes, gets a result back from the environment to see what impact the action has had on the environment. So for example, if the AC turned the cooling on, that's an action that the air conditioning system took. Now the impact will be the temperature of the room will come down. So my air conditioner will determine whether to keep the cooling on or turn the cooling off based on the feedback it is getting from the environment. If the temperature has become lower than the desired level, that means the cooling should be turned off. If it is not yet on the desired level, the cooling should remain on. So this is how my control systems work, right? Basically, what happens is that it takes some user interface for us, allowing for us users to interact. It takes inputs from the environment using some digital or analog sensors. If it's analog input, then it is sensors. The embedded system will work with these two values and produce some sort of output. Our air conditioner performs an output by turning on the fan or turning on the compressor, so on and so forth. So this is an example of embedded system. Our embedded systems can be programmable versus non-programmable. If it is a programmable device, that means At some point, if I want to change some features of my embedded system, I can change them. But if it is non-programmable device and I want to add new features to my whole hardware system, I will have to change the embedded system completely. I have to change the processor. I have to change the onboard circuitry if it's a non-programmable device. So non-programmable devices are obsolete, by the way. I mean, right now we have most embedded systems can be reprogrammed, but in previous times, older generations, we had devices that had onboard embedded systems, but they were non-programmable. In which case, to add additional features or make some improvements in a hardware system, we had to completely replace the embedded system on board. Okay, so this is a difference. Currently, the modern generation of embedded systems allow reprogramming, but reprogramming can be carried out in two ways. For example, I can choose to connect my embedded system with a computer and download my new updated data to the embedded system through some USB or other connecting port. That's normal. For example, you can program your car's onboard processor to say, burn fuel in a different way or operate the fuel injectors in a different way. You can reprogram your cards on board a computer to change how it works. And the way we do that, we have to connect specialized hardware as well as your computer to reprogram your onboard car's computer. But it can be reprogrammed, but the method is different. It does it through some connecting to the computer, right? On the other way, there's another way of updating your embedded system is through OTA, over the air transmission. So basically what happens is that computer, that embedded system, if it's capable of connecting to a wireless network, it simply downloads the updates and reinstalls them on its own, right? So for example, your smartphones do this. Whenever there's a new operating system or there's an update to the operating system, it updates itself over the air. So basically, this is over the air updating, right? So updates, if it's a programmable embedded system, it can be carried out in two ways. One, you can be connected to a computer via some wired link, or you can do it wirelessly through some wireless over the air data transmission, either from Wi-Fi or cellular network, whatever it is. There are some advantages versus disadvantages versus embedded systems. Benefits are they are very small in size. That means we can incorporate them into smaller and smaller devices, making them smart devices. They can be compared to other systems. They are relatively cheap to make, so we can incorporate them to multiple devices as well. They are usually dedicated to one task, allowing simple interfaces and offer no requirement for an operating system. So operating system means that we have introduced multiple features. Since they're only carrying on one task, as opposed to our general purpose computer that you're currently reviewing this video on, as opposed to that, it is supposed to be only carrying out a single task. So you don't need an operating system. It doesn't need large storage, large RAM. They consume very little power, and they have a very efficient small processor, small hardware, because it doesn't have to perform that many tasks. They can be controlled remotely using mobile phone. For example, modern air conditioners are capable of being connected through mobile phones, through either infrared or through Wi-Fi connections. Very fast reaction changing input, operate in real time, and feedback is oriented. Real time processing means that my system reacts to changes before the environment has a chance to change again. So basically, if, for example, I am sitting in an air conditioner room, that there is a real-time processing system. It does not involve my input to work. It simply carries out its own processing based on the inputs it's getting from the environment. It changes in real time. If the temperature is going down, and the air's AC or air conditioner is responding according to that changing temperature. If the temperature is going up, it responds accordingly. It does not require my help in any way. It's simply working on its own. As long as it's given power supply, as long as it is connected to an active power supply, it will continue to work without my involvement. With mass production comes reliability. After all, you get newer and new with more production of the same chipset, you will eliminate bugs and eventually lead to more optimized, better versions of the same system, lesser errors. So later versions will be more perfect. And if you have following the same chipset for a long time, you know that over generations it has been perfected and there's no errors in it. Let's look at the drawbacks again. It can be difficult to upgrade some devices to make advantage of new technology. You need specialized devices. For example, let's go back to our car fuel injection system. It needs a specialized computer to connect to it. It doesn't connect to just any other computer. It needs a specialized port and a specialized computer to operate, connect to that computer, to that onboard fuel injection system of a car. Troubleshooting faults in devices becomes a specialist task. Only specific people who are trained to operate on the embedded systems can do it. Not every person can handle it. You can't simply just go on the Google and search a method for solving a problem. No, you have to have a specialist to do it. And if it's done wrong, the embedded system can be corrupted forever. Although interface can appear to be more simple, it in reality it can be more confusing. For example, changing times in a cooker clock can require several steps. So as opposed to our mouse cursor and the simpler GUI that is made available to you on a general purpose computer, embedded systems do not have such facilities, and simple settings of timers and stuff like that becomes quite a difficult task. Any device that can be accessed over the internet can also is open to hackers and viruses and stuff. And the thing here is, let's just say take our wireless what you call it, our air conditioner system, for example. I can control that through my Wi-Fi connection. That means that air conditioner has to be connected to my internet, to my Wi-Fi. I can connect it from outside my home, because if I'm connected to the internet, the air conditioner is connected to the internet, we can communicate. But the problem is that conventionally, when I have a general purpose computer, my laptop, for example, connected to the internet, I am under the protection of firewalls and antivirus and so on and so forth. And that is allowed because I have a complex hardware, onboard hardware. I have a complex CPU, I have a complex storage, I have a bigger RAM, I have a bigger hard disk. These things are not available to embedded systems. Embedded systems have simple processes. They don't have big storage. They don't even have an operating system, in which case they are not capable of having onboard antiviruses to run on them. So in that case, this embedded system, even though my air conditioner is connected to the internet, it is not protected the same way as I am, in which case that it is more vulnerable to internet security threats. Due to difficulty in upgrading, a fault finding devices are often just thrown away rather than being used, which results in very it's not environmentally friendly, because I cannot reuse devices. I simply discard them. So uh, it's good that I should upgrade them. I should, instead of just throwing them, I should be able to update them and make use of the same hardware instead of investing in new hardware. So it's actually a wasteful process that you have to replace these chips. Second, finally, can lead to an increase in the throwaway society if devices are discarded just because they have become out of date. Now, this is again linked to this aspect. It leads to more electronic waste, resulting in more pollution, right? Now, embedded systems can be connected to the internet. It is possible to control them remotely, like we mentioned, the air conditioners, and their application can range from MP3 player to very complex medical imaging systems. Since they are required to perform limited set of activities, they can be made physically small. They can be very small devices and very large devices as well. Apart from that, there are some examples mentioned here regarding the embedding systems. We have set-top boxes that are allowing to control your recording of live transmissions on the TV. Set-top controller, it requires some input from your cable. It does the controller manages how data is stored in your SSD versus what data is stored in the RAM, and simply it is an easy way to store data that is being played back on your TV. Apart from that, we have security system, which is also an monitoring system that relies on onboard processors and sensors and pre-stored data that can be entered through some keypad interface. For example, the security logs and whatever that you want to enter, the security system allows that. So once you enter the security log, the security system becomes active, and any intruder that enters the system will be stopped right then and there. The output in some sort of sirens and alarms and lights and stuff like that, the security system produces that. It is a very good example of that. Apart from that, vending machine that allows you to simply select a particular item, for example, soft drink that you want, you simply select the soft drink from the display, and it simply takes the input of money. The money should be according to the selection that you made. It calculates whether the selection and the money amount are same. If there is change to be returned, it will return the change. And if the money that you've entered is not, what you call it, enough for the vending machine, it will discard the amount. It may even present you with an accurate message. In fact, it is in modern vending machines are very capable of determining whether or not you've entered a fake currency. So they can predict discarded notes or corrupted notes or fake notes, and they should, it's a very complex, a very good system that is capable of detecting fake notes as well. But it requires a microcontroller in between, right? So based on the currency you enter, amount that you enter, if the amount is okay, then it should simply return the product that you have selected on the some slot from underneath the machine, and you can pick it up from there. But this is a very complete system that allows the display of prices and the actuators that allow for the particular product to reach your the slot for you to receive. And if it is for example something that has to be maintained in a controlled temperature, for example sandwiches or soft drinks, the onboard temperature sensors maintain that specific temperature. So it's a very complex system that requires many inputs of sensors and actuators and other processing systems that can make this system complete vending machine work. Apart from that, lighting automatic light systems rely on the concept of how much sunlight is coming in. If the sunlight is getting dim, lesser and lesser, that means we're moving towards the night, and the light system will determine whether to turn on the lights. So it will also be able to differentiate if the light difference is very short. For example, you have a cloud, very dark cloud appearing in front of the sun for a very small time. That does not mean the light should be turned on because the duration was very small. But if it is a long duration for the direction, so for example 5-10 minutes, that means it really is nighttime, in which case my light will turn on. So my onboard lighting securing system is basically maintaining that. Finally, washing machines is a very good example. Washing machines allow for keypads in which you can select the time, the type of washing, the temperature of washing, possibly the the wash predefined wash cycles, whatever it is, you can select that, and the onboard processing system maintains that exact specifications that you input. Based on the temperature sensors, it maintains a certain temperature while washing. There's an onboard timer that controls how long the washing should be taken. There's an onboard moisture sensor that basically allows for tumble dry as well. So these are very complex. They're not that complex, but they can do this task very simply. As defined for embedded systems, they are capable of carrying out specific tasks very accurately. And washing machines and set-top boxes, lighting system, vending machines, security systems, they're all very good examples of embedded systems. So look around you. How many embedded systems do you see around you? So how do they operate? What types of sensors and inputs do they require? Do you think it's a microcontroller or systems on chip or a microprocessor? What is it? Now, look around you. I'm pretty sure there will be many embedded systems around you.